Hello everyone, welcome back. Today we're going to talk about element number 65, terbium. Terbium itself, and to an even greater degree, a particular alloy of terbium, called terfenol, has the unusual property of changing shape when placed in a magnetic field. A rod of the stuff will instantaneously grow longer or shorter by a small amount depending on the strength and alignment of the field it's in. This property might not seem very useful, but you can use it to turn any solid surface into a loudspeaker. If you press the end of a terfenol rod down on a wooden tabletop, then apply a magnetic field whose strength follows an audio signal by wrapping the terfenol rod in what amounts to a speaker coil, the rod will shake the whole table, turning its entire surface into a huge sound-radiating surface that plays the same role as a speaker cone. Why not just press an ordinary loudspeaker onto the table and get the same effect? Because that will just muffle the speaker. This is an example of the problem of impedance matching. Ordinary speakers exert a small force to move a lightweight speaker cone over a relatively large distance. In order to move the large mass of a solid wood tabletop, a large force must be exerted over a short distance, which an ordinary speaker magnet and coil just can't do. A terfenol rod is one of the very few ways to make this type of loudspeaker, and you can actually buy fairly inexpensive terfenol devices designed for exactly this purpose. If only dysprosium had such a wide spectrum of uses. Terbium, element number 65, the lanthanoid elements. Its symbol is Tb, its atomic number is 65, its atomic weight is 158.93, its color is silver white, its standard state is solid at 25 degrees Celsius or 77 degrees Fahrenheit. Its classification is metallic. Terbium or not terbium? That is the question. Well, let's find out. Stick me in a magnetic field and watch me writhe and wriggle. Compounds made with me have the strange ability to change their length when magnetized. This funky property is used to create terbium-charged devices that make any flat surface act as a speaker. Its density is 8.19 grams per centimeters cubed. Its melting point is 1,356 degrees Celsius or 2,473 degrees Fahrenheit. Its boiling point is 3,230 degrees Celsius or 5,846 degrees Fahrenheit. Its chemical symbol is Tb. Terbium's date of discovery was in 1843. And here we have a map of 1843 CE. Terbium, element number 65, chemical symbol Tb. Terbium was discovered by Swedish chemist Carl Mosander, who detected it as an impurity in yttrium oxide. It's one of 4 elements named after the tiny Swedish village of Ytterby. The others are erbium, yttrium, and ytterbium, and all were isolated from gadoliniite, which was mined there. Because of their similarities, the elements were confused in the 19th century, and the names of erbium and terbium ended up switched. Today, terbium is used in fuel cells, in special alloys, and to make some types of fluorescent lamps. Terbium, element number 65, again, chemical symbol Tb. Pure terbium is soft enough to cut with a knife. Some of its compounds are used to line mercury lamps. When electrified, mercury vapor inside these lamps gives off ultraviolet light, which turns bright yellow due to terbium. Its atomic mass is 158.925, its state is a solid, and its date of discovery was in 1843 by Carl Gustav Mosander. In the 19th century, scientists got confused between terbium and erbium and accidentally switched their names. Here we have a laboratory sample of pure terbium. And yes, even scientists make mistakes. So again, pure terbium is soft enough to cut with a knife, chromium knife. Again, when electrified, mercury vapor inside these lamps gives off ultraviolet light. That's the ultraviolet light. And then the bulb is coated with terbium, so the ultraviolet light becomes yellow because of the terbium coating around the bulb. Terbium, element number 65, chemical symbol Tb. Sonar. Terfenol-d, a terbium alloy, changes shape in magnetic fields and is used in naval sonar systems and sensors. Green light. Green terbium phosphors provide the green light in many screens and are also used in trichromatic lighting. Triboluminescent. Some terbium compounds are triboluminescent, emit light when fractured. They could be used in sensors. So what is terfenol-d used for? For example, terfenol-d was first used to make underwater acoustic devices in naval sonar systems, and has since been introduced as a new technology for fuel injectors in diesel engines, where the expansion or contraction of this alloy regulates the flow of fuel through the injector, according to www.instituteofmaking.org.uk. Terfenol-d, Materials Library, Institute of Making. We mentioned impedance matching. Impedance matching is designing source and load impedances to minimize signal reflection or maximize power transfer. In DC circuits, the source and load should be equal. In AC circuits, the source should either equal the load or the complex conjugate of the load, depending on the goal. According to www.analog.com, Designer Center Glossary, definition of impedance matching, analog devices. Here we have the typical actuator cross-section with the permanent magnets, the terfenol-d drive rod here, and the coil with the preload springs and the output rod. Again, impedance matching in electronics. Impedance matching is the practice of designing or adjusting the input impedance or output impedance of an electrical device for a desired value. Often, the desired value is selected to maximize power transfer or minimize signal reflection, according to Wikipedia. Here we have a rod of terfenol alloy inside a copper coil, and it creates a solid surface audio driver. Here we have a slice of pure solid terbium, element number 65. Here we have a vacuum distilled crystal terbium plate. Here we have a bumpy rod of very high purity terbium, and terbium doped red glass decorative teardrop. Going back, again, terbium was discovered by a Swedish chemist, Carl Mosander, who detected it as an impurity in yttrium oxide. We talked about yttrium in a previous video. Feel free to check out that video. I'll leave a link in the description below to learn about yttrium oxide. Carl Gustav Mosander, Swedish chemist. Carl Gustav Mosander was a Swedish chemist. We previously talked about him in the yttrium video. He discovered the rare earth elements lanthanum, erbium, and terbium, according to Wikipedia. He discovered lanthanum, erbium, terbium, and cerium. We'll talk about the element lanthanum and erbium. We're currently talking about the element terbium, and we'll talk about the element cerium in a future video as well. And they do sound familiar. It could be confusing to distinguish them. Not to worry. In the 19th century, scientists also got confused between terbium and erbium and accidentally switched their names. Let's continue with the element terbium, element number 65. Terbium is used to dope calcium fluoride, calcium tungstate, and strontium molybdate, all used in solid-state devices. It is also used in low-energy light bulbs and mercury lamps. It has been used to improve the safety of medical X-rays by allowing the same quality image to be produced with a much shorter exposure time. Terbium salts are used in laser devices. Pew! An alloy of terbium, dysprosium, and iron lengthens and shortens in a magnetic field. This effect forms the basis of loudspeakers that sit on a flat surface, such as a window pane, which then acts as the speaker. Terbium, TB. Terbium is a vital ingredient of magnetorestrictive alloys, which change their length when they are exposed to a magnetic field. Such alloys are used in specialized loudspeakers designed to push against solids rather than against air. Like most of the lanthanides, terbium metal readily ignites in air when provoked sufficiently with a hot flame. So terbium is used to dope calcium fluoride, calcium tungstate, and strontium molybdate. Terbium is used within an X-ray machine to allow the exposure time to be much shorter while giving the same quality image that is necessary for diagnosis. According to study.com, Academy lesson, what is terbium? What is terbium? Uses, facts, and chemical properties. Terbium-3 fluoride, chemical compound. Terbium-3 fluoride is an inorganic compound with chemical formula TbF3. It is hard to dissolve in water. It can be produced by reacting terbium-3 carbonate and 40% hydrofluoric acid at 40 degrees Celsius, according to Wikipedia. Its ChemSpider ID is 496. Its chemical formula is TbF3. Its melting point is 1172 degrees Celsius. Terbium fluoride. 1 atom of terbium bound to 3 atoms of fluorine. Terbium-3 chloride. Chemical compound. Terbium-3 chloride is a chemical compound. In the solid state, TbCl3 has the YCl3 layer structure. Terbium-3 chloride frequently forms a hexahydrate, according to Wikipedia. Its molar mass is 265.2834 grams per mole. Its formula is TbCl3. Its melting point is 1036 degrees Fahrenheit or 558 degrees Celsius. Its density is 4.35 grams per centimeters cubed. Its ChemSpider ID is 55380. Its solubility in water is soluble. Its boiling point is 180 to 200 degrees Celsius, or 356 to 392 degrees Fahrenheit, 453 to 473 degrees Kelvin, in HCl gas atmosphere. Here we have terbium-3 chloride. 1 atom of terbium bound to 3 atoms of chlorine. Terbium-3 bromide. Chemical compound. Terbium-3 bromide is a crystalline chemical compound, according to Wikipedia. Its formula is TbBr3. Its melting point is 1522 degrees Fahrenheit or 828 degrees Celsius. Its density is 4.67 grams per centimeters cubed, and its molar mass is 398.637 grams per mole. Here we have terbium bromide. 1 atom of terbium bound to 3 atoms of bromine. Terbium-3 iodine. Chemical compound. Terbium-3 iodide is an inorganic chemical compound, according to Wikipedia. Its formula is TbI3. Its density is 5.2 grams per centimeters cubed. Its melting point is 1755 degrees Fahrenheit or 957 degrees Celsius. Its molar mass is 539.638 grams per mole, and its crystal structure is hexagonal. Here we have terbium iodide, which consists of 1 atom of terbium and 3 atoms of iodine. Here are the animations. Terbium compounds are used as green phosphors in fluorescent lamps, computer monitors, and TV screens that use cathode ray tubes. Another major use is with dysprosium and iron in the magnetorestrictive alloy terfenol-d, which consists of the elements terbium, dysprosium, and iron. The specific chemical formula is Tb0.3 dy0.7 Fe2. That is the ratio of the alloy, which is a component of magnetically controlled actuators, sonar systems, and pressure sensors. Together with another lanthanide, gadolinium, terbium was used by Geoffrey Green and co-workers in 1990 to build a dual-stage room-temperature magnetic refrigerator prototype, with gadolinium as a high-temperature stage and terbium as a low-temperature stage. That is called magnetic cooling. Magnetic refrigerators use gadolinium. Its temperature drops when it's removed from a magnetic field. Terbium has no known biological role. It has low toxicity. History. Terbium was first isolated in 1843 by the Swedish chemist Carl Mosander at Stockholm. He had already investigated cerium oxide and separated a new element from it, lanthanum, and now he focused his attention on yttrium, discovered in 1794, because he thought this too might harbor another element. In fact, Mosander was able to obtain 2 other metal oxides from it, terbium oxide, yellow, and erbium oxide, rose pink, and these he announced in 1843. This was not the end of the story, however, because later that century, these 2 yielded other rare earth elements, aka lanthanoids. Today, these elements are easily separated by a process known as liquid-liquid extraction. Liquid-liquid extraction, talked about in previous videos, also known as solvent extraction and partitioning, is a method to separate compounds or metal complexes based on their relative solubilities in 2 different immiscible liquids, usually water and an organic solvent, according to Wikipedia. Here we have some information on Geoffrey L. Green and Carl Gustav Mosander. Geoffrey L. Green, physicist. Geoffrey L. Green is an American neutron physicist. Green received his bachelor's degree from Swarthmore College in 1971 and his doctorate from Harvard University in 1974 with Norman Ramsey, a Nobel laureate in physics. There he worked on low-energy neutrons, which were then first available in intense beams, according to Wikipedia. His education was Harvard University at Swarthmore College. Carl Gustav Mausender. The element was discovered in 1843 by Swedish chemist Carl Gustav Mausender in a heavy rare earth fraction called yttria, but its existence was not confirmed for at least 30 years, and pure compounds were not prepared until 1905. Here we have a map of 1943 CE, the date that Carl Gustav Mausender discovered element number 65, and here we have a map of 1905, the year in which element number 65 was purified. Terbium occurs in many rare earth minerals, but is almost exclusively obtained from bastnasite and from laterite ion exchange clays. Bastnasite. The mineral bastnasite is one of a family of 3 carbonate fluoride minerals, which includes bastnasite with a formula of CO3F, bastnasite with a formula of CO3F, and bastnasite with a formula of CO3F, the same formula. Some of the bastnasites contain OH negative instead of F negative and receive the name of hydroxyl bastnasite. Its color is honey yellow, reddish brown. Its specific gravity is 4.95 through 5.0. Its cleavage is imperfect to indistinct on, parting on. Its crystal class is ditriagonal dipyramidal 6M2 HM symbol 6M2. Its crystal system is hexagonal. Its formula is repeating unit lanthanum, cerium, yttrium, carbon, oxygen, fluorine. Its IMA symbol is BSN. Here we have lanthanum, cerium, yttrium, carbon, oxygen, and fluorine. It is also found in the products of nuclear fission. Terbium is one of the least abundant of the rare earths. Its abundance in Earth's crust is about the same as thallium. Element number 81. We previously talked about that element. I'll leave a link in the description below if you're interested in learning about that element, although it could be subject to errors. Terbium, Tb, chemical element, a rare earth metal of the lanthanide series of the periodic table. Terbium is a moderately hard, silvery white metal that is stable in air when in pure form. The metal is relatively stable in air even at high temperatures because of formation of a tight, dark oxide layer that can be represented as a mixed oxide composed of Tb2O3 and TbO2. Terbium readily reacts with diluted acids, but it is insoluble in hydrofluoric acid, HF, because the presence of the fluoride ion protects the metal from further reaction by forming a protective layer of TbF3. So here's the formula. Just a quick sketch. Tb plus HF will make TbF3 plus H2. This is the unbalanced formula. This is live, so excuse my messy handwriting. Let's balance the formula. I use a calculator called ChemEquate to balance the formula, but if you guys would like me to make a video on how to balance the equation without a calculator, let me know. I can make a separate video on how to balance chemical equations without a calculator. But in this case, let's enter it. So the balanced chemical formula for this is 2Tb plus 6HF 2Tb F3 plus 3H2 balanced. And this is what happens when hydrofluoric acid interacts with the terbium metal. Hydrofluoric acid is a solution of hydrogen fluoride in water. Solutions of HF are colorless, acidic, and highly corrosive. It is used to make most fluorine-containing compounds. Examples include the commonly used pharmaceutical antidepressant medication fluoxetine and the material PTFE, according to Wikipedia. Again, its formula is HF. Its melting point is negative 118.4 degrees Fahrenheit or negative 83.55 degrees Celsius. Its molar mass is 20.0063 grams per mole. Its boiling point is 67.1 degrees Fahrenheit or 19.5 degrees Celsius. Its appearance is a colorless liquid, and its 3D model JSMOL interactive image acidity over pKa is 3.17. So again, the metal is stable in air at high temperatures because of the formation of a tight dark oxide layer. I created two separate types of oxides of terbium, but they're actually a fusion of the two, and it's a variation of TB2O3 and TbO2 oxide layer. The metal is a very strong paramagnet above 230 Kelvin, negative 43 degrees Celsius, or negative 46 degrees Fahrenheit. It is antiferromagnetic between 220 Kelvin, negative 53 degrees Celsius, or negative 64 degrees Fahrenheit, and 230 Kelvin. And it becomes ferromagnetic below 220 Kelvin. What is a paramagnet? Paramagnetism is a form of magnetism whereby some materials are weakly attracted by an externally applied magnetic field and form internal induced magnetic fields in the direction of the applied magnetic field, according to Wikipedia. What is antiferromagnetism? In materials that exhibit antiferromagnetism, the magnetic moments of atoms or molecules, usually related to the spins of electrons, align in a regular pattern with neighboring spins pointing in opposite directions. This is, like ferromagnetism and ferrimagnetism, a manifestation of ordered magnetism, according to Wikipedia. Ferromagnetism is a property of certain materials that results in a significant observable magnetic permeability, and in many cases a significant magnetic coercivity, allowing the material to form a permanent magnet, according to Wikipedia. The molecules mentioned in this slide are terbium oxide, hydrofluoric acid, and terbium fluoride. Terbium-3 oxide, chemical compound. Terbium-3 oxide, also known as terbium sesquioxide, is a sesquioxide of the rare earth metal terbium, having chemical formula Tb2O3. It is a p-type semiconductor which conducts protons, which is enhanced when doped with calcium. It may be prepared by the reduction of Tb4O7 in hydrogen at 1,300 degrees Celsius for 24 hours, according to Wikipedia. Its molar mass is 365.85 grams per mole. Its formula is Tb2O3. Its density is 7.9 grams per centimeters cubed. Its ChemSpider ID is 140187. Its melting point is 2,410 degrees Celsius or 4,370 degrees Fahrenheit or 2,680 degrees Kelvin. Its crystal structure is cubic, Cl80. Its Gibbs free energy is negative 1,776.553 kilojoules per mole. Terbium-3 fluoride, chemical compound. Terbium-3 fluoride is an inorganic compound with chemical formula TbF3. It is hard to dissolve in water. It can be produced by reacting terbium-3 carbonate and 40% hydrofluoric acid at 40 degrees Celsius, according to Wikipedia. Its ChemSpider ID is 75496. Its chemical formula is TbF3. Its melting point is 1,172 degrees Celsius. Here we have some more information on antiferromagnetism. I'll make a future video in which we talk about different types of magnetisms that exist. There's ferromagnetism, antiferromagnetism, paramagnetism, and all of those sound similar, but I'll make a video that'll explain the concept of the different types of magnetisms in order to clarify and lead to greater understanding of magnetism overall. Let's continue with element number 65, chemical symbol Tb. The only isotope occurring in ores is terbium-159. A total of 36, excluding nuclear isomers, radioactive isotopes of terbium have been identified. Their mass ranges from 135 to 171, with half-life ranging from more than 200 nanoseconds terbium-138, to 180 years, terbium-158. And again, there's a total of 38 nuclear isomers, radioactive. Only one isomer is not radioactive, terbium-159. As you can see, it doesn't have a half-life or a mode of decay, but the other 36 are. Solvent-solvent extraction and ion exchange techniques are utilized for commercial production of terbium. The metal is prepared in a highly pure form by metallothermic reduction of the anhydrous fluoride with calcium metal to produce terbium and calcium fluoride. Here we have the unbalanced and balanced chemical equations. Terbium exists in three allotropic structural forms. The alpha phase is close-packed hexagonal with A is equal to 3.6055 angstroms and C is equal to 5.6966 angstroms at room temperature. The ferromagnetic ordering below 220 Kelvin is accompanied by an orthorhombic distortion of the hexagonal lattice to the beta phase with A is equal to 3.605 angstroms, B is equal to 6.244 angstroms, and C is equal to 5.706 angstroms at 77 Kelvin. Negative 196 degrees Celsius or negative 321 degrees Fahrenheit. The Y phase or gamma phase is body-centered cubic with A is equal to 4.07 angstroms at 1,289 degrees Celsius or 2,352 degrees Fahrenheit. Terbium is one of a few rare earths that have a +4 as well as a +3 oxidation state. The former is a result of stability of the half-filled 4F shell. The brown oxide, prepared by air ignition, has the approximate formula Tb4O7. Here we have Tb4O7, 4 atoms of terbium, 1, 2, 3, 4, 5, 6, 7 atoms of oxygen. Here we have the animation. Again, this is prepared by air ignition. The reason I say that is because the oxide TbO2 is the balance formula of Tb4O7, but the oxide is obtained by using atomic oxygen, which means it's just oxygen on its own. Oxygen molecules, 2 oxygen atoms bonded together as O2, decompose into 2 separate oxygen atoms, or atomic oxygen. Because the unpaired atoms react very easily with other materials, they are very destructive to spacecraft and satellites, but very beneficial for cleaning surfaces on Earth, according to www.nasa.gov. Utilizing atomic oxygen, Tb plus oxygen creates TbO2. Here we have the corrections. TbO2. The tetrafluoride TbF4 is prepared by fluorinating the trifluoride. The Tb4+ ion is not known in solution. In other salts and in solution, terbium is present in the +3 oxidation state and behaves as a typical rare earth. Its solutions are pale pink to colorless. Natural abundance. Terbium can be recovered from the minerals monazite and basnecite by ion exchange and solvent extraction. It is also obtained from euxenite, a complex oxide containing 1% or more of terbium. The metal is usually produced commercially by reducing the anhydrous fluoride or chloride with calcium metal under a vacuum. So here we have the balance formula, terbium trifluoride with calcium. This is the balance formula, produces terbium and calcium trifluoride. And here we have the unbalanced and balanced formula, and for terbium 3 chloride with calcium to produce terbium and calcium chloride. Unbalanced and balanced formula. All of these reactions occur under a vacuum. Low pressures are needed in order for the reaction to take place. So you can't do this under stable atmospheric conditions. It is also possible to produce the metal by the electrolysis of terbium oxide in molten calcium chloride. So here we have molten calcium chloride. The battery, the cathode, and the anode. The terbium would go to the cathode. Since the cathode is negative, it attracts the positive ions. And the anode is positive, it attracts the negative ions. In this case, oxygen. Visual elements image. The abstracted compact disc symbol reflects the use of the element in the manufacture of the first rewritable compact discs. Seen here. So all Terbium explained in X minutes or less and as a short amount of time as possible. We thank you for watching. Once again, if you like this video, make sure to like, comment, subscribe. Other than that, have a great one.